ਮਾਰੀ ਗੋਰੀਏ ਨੀ ਸੱਚੀ ਉਦੋਂ ਦਿਸਦੇ ਸਿਤਾਰੇ ਗੋਰੀਏ ਉਹ ਸੰਗ ਦੀ ਤੇ ਜ਼ੁਲਫਾਂ ਨਾਲ ਫਿਰੇ ਖੇਡਦੀ ਹੈ ਪੂਰਾ ਨੀ ਤੂੰ ਕਹਿਰ ਗੁਜ਼ਾਰੇ ਗੋਰੀਏ ਫੋਟੋਆਂ ਤੇ ਪਾਵੇ ਜੋ ਸਟੋਰੀਆਂ ਹੈ ਦਿਲ ਕਰੇ ਤੈਨੂੰ ਬਾਰ-ਬਾਰ ਤੱਕ ਲਾਂ ਕਿਤੇ ਹੋ ਨਾ ਜਾਵੇ ਦੂਰੀ ਇਸ ਗੱਲ ਤੋਂ ਡਰਾਨੀ ਤੈਨੂੰ ਸੋਹਣੀਏ ਮੈਂ ਦਿਲ 'ਚ ਲਗਾ ਕੇ ਰੱਖ ਲਾਂ ਗੀਤ ਦੀਆਂ ਲਿਖਤਾਂ 'ਚ ਤੇਰਾ ਹੀ ਜ਼ਿਕਰ ਸੱਚੀ ਖੁਦ ਨਾਲੋਂ ਜ਼ਿਆਦਾ ਕਰੇ ਤੇਰਾ ਹੀ ਫਿਕਰ ਜਿਹੜਾ ਬਚਦਾ ਸੀ ਬਿੱਲੋ ਇਹਨਾਂ ਕੰਮਾਂ ਤੋਂ ਨਹੀਂ ਬਸ ਤੇਰੀ ਸੰਗ ਕੋਲੋਂ ਹਾਰੇ ਗੋਰੀਏ ਹੈ ਲੰਘਦੀ ਨੇ ਅੱਖ ਸੀ ਜੋ ਮਾਰੀ ਗੋਰੀਏ ਇਹ ਸੱਚੀ ਉਦੋਂ ਦਿਸਦੇ ਸੀ ਤਾਰੇ ਗੋਰੀਏ ਉਹ ਸੰਗ ਦੀ ਤੇ ਜ਼ੁਲਫਾਂ ਨਾਲ ਫਿਰੇ ਖੇਡਦੀ ਹੈ ਪੂਰਾ ਨੀ ਤੂੰ ਕਹਿਰ ਗੁਜ਼ਾਰੇ ਗੋਰੀਏ ਹਾਂ ਲੰਘਦੀ ਨੇ ਅੱਖ ਸੀ ਜੋ ਮਾਰੀ ਗੋਰੀਏ ਇਹ ਸੱਚੀ ਉਦੋਂ ਦਿਸਦੇ ਸੀ ਤਾਰੇ ਗੋਰੀਏ ਉਹ ਸੰਗ ਦੀ ਤੇ ਜ਼ੁਲਫਾਂ ਨਾਲ ਫਿਰੇ ਖੇਡਦੀ ਹੈ ਪੂਰਾ ਨੀ ਤੂੰ ਕਹਿਰ ਗੁਜ਼ਾਰੇ ਗੋਰੀਏ
ਕੋਲ ਹੀ ਹੈ ਤੂੰ ਤਾਂ ਵੀ ਲੱਗੇ ਮੈਨੂੰ ਦੂਰ ਸੋਚਾਂ ਕਿਉਂ ਮੈਂ ਏਦਾਂ ਕੋਈ ਗੱਲ ਤੇ ਜ਼ਰੂਰ ਜ਼ਰਾ ਪੁੱਛ ਕੇ ਤੂੰ ਦੱਸ ਕੀ ਨਹੀਂ ਕੀ ਇਹ ਸੱਚ ਮੇਰੇ ਦਿਲ ਨੂੰ ਰਾਤਾਂ ਨੂੰ ਦੱਸ ਮੈਨੂੰ ਨੀਂਦ ਕਿਉਂ ਨਾ ਆਵੇ ਤੂੰ ਠੀਕ ਹੈ ਕਿ ਨਹੀਂ ਮੇਰਾ ਚਿੱਤ ਘਬਰਾਵੇ ਕਿਉਂ ਇੰਨੀ ਪਰਵਾਹ ਨਾ ਦੇਵੀਂ ਤੂੰ ਦਗਾ ਮੇਰੇ ਦਿਲ ਨੂੰ ਤਾਂ ਮੈਂ ਗੁਨਾਹ ਜ਼ਰਾ ਹਾਲ ਤੇ ਸੁਣਾ ਮੇਰੇ ਭਟਕਦੇ ਦਿਲ ਨੂੰ ਕਿਉਂ ਦਿੱਤੀ ਸੀ ਪਨਾਹ ਕਿਉਂ ਇੰਨੀ ਪਰਵਾਹ ਨਾ ਦੇਵੀਂ ਤੂੰ ਦਗਾ ਮੇਰੇ ਦਿਲ ਨੂੰ ਕੋਲ ਹੀ ਹੈ ਤੂੰ ਤਾਂ ਵੀ ਲੱਗੇ ਮੈਨੂੰ ਦੂਰ ਸੋਚਾਂ ਕਿਉਂ ਮੈਂ ਏਦਾਂ ਕੋਈ ਗੱਲ ਤੇ ਜ਼ਰੂਰ ਜ਼ਰਾ ਮੇਰੇ ਦਿਲ ਨੂੰ ਹੋਣ ਦਾ ਖਿਆਲ ਵੀ ਮੇਰਾ ਕੋਈ ਖਿਆਲ ਨਾ ਜੋ ਲੱਗੇ ਉਹੀ ਦੱਸਾਂ ਜਿਹੜਾ ਕੀਤਾ ਆ ਮੈਂ ਮਸਾਂ ਨੀ ਤੂੰ ਪੁੱਛਦੀ ਸਵਾਲ ਨਾ ਤੂੰ ਜਦੋਂ ਮਿਲੀ ਲੱਗਿਆ ਸੀ ਮੈਨੂੰ ਕਿਸੇ ਚੀਜ਼ ਦੀ ਪਾਲਨਾ ਮੇਰੀ ਬਣ ਕੇ ਤੂੰ ਦੁਨੀਆ ਦਿਲ ਜਾ ਤਾਂ ਰੱਖ ਐਵੇਂ ਗੱਲਾਂ ਵਿੱਚ ਟਾਲਣਾ ਸਮਝਾਵਾਂ ਕਿ ਅੱਖ ਕੇ ਮਨਾਵਾਂ ਜੋ ਲੰਘਿਆ ਏ ਸਮਾਂ ਉਹਨੂੰ ਕਿੰਜ ਮੈਂ ਪਲਾਵਾਂ ਜਿਉਂ ਇੰਨੀ ਪਰਵਾਹ ਨਾ ਤੂੰ ਦੇ ਜਿਵੇਂ ਦਗਾ ਮੇਰੇ ਦਿਲ ਨੂੰ ਕੋਲ ਹੀ ਹੈ ਤੂੰ ਤਾਂ ਵੀ ਲੱਗੇ ਮੈਨੂੰ ਦੂਰ ਸੋਚਾਂ ਕਿਉਂ ਮੈਂ ਏਦਾਂ ਕੋਈ ਗੱਲ ਤੇ ਜ਼ਰੂਰ ਪੁੱਛ ਕੇ ਤੂੰ ਦੱਸ ਕੀ ਆਣ ਕੀ ਹੈ ਸੱਚ ਮੇਰੇ ਦਿਲ ਨੂੰ ਗੱਲ ਤੇ ਯਕੀਨ ਨਾ ਰਿਹਾ ਸਾਡਾ ਪਿਆਰ ਵੀ ਰੰਗੀਨ ਨਾ ਰਿਹਾ ਕਿਤੇ ਬੱਦਲ ਬਾਈ ਆਈ ਤੰਗ ਤਨਹਾਈ ਹੋਵਾਂ ਹਵਾ ਮੈਂ ਜ਼ਮੀਨ ਨਾ ਰਿਹਾ ਅਸੀਂ ਕੱਲੇ ਰਹਿ ਜਾਣਾ ਸਾਨੂੰ ਗਮਾਂ ਲੈ ਜਾਣਾ ਅਸੀਂ ਹੋ ਜਾਣਾ ਪੁਰਾਣੇ ਸਭ ਚੁੱਪ ਕਹਿ ਜਾਣਾ ਉੱਥੇ ਤੂੰ ਵੀ ਨਹੀਂ ਹੋਣਾ ਕਿਸੇ ਹੱਥ ਨਾ ਫੜਾਉਣਾ ਬਸ ਯਾਦਾਂ ਨੇ ਪੈ ਜਾਣਾ ਕੋਲ ਹੀ ਹੈ ਤੂੰ ਤਾਂ ਵੀ ਲੱਗੇ ਮੈਨੂੰ ਤੂੰ ਸੋਚਾਂ ਕਿਉਂ ਮੈਂ ਏਦਾਂ ਕੋਈ ਗੱਲ ਤੇ ਜ਼ਰੂਰ ਜ਼ਰਾ ਪੁੱਛ ਕੇ ਤੂੰ ਦੱਸ ਕੀ ਨਹੀਂ ਕੀ ਇਹ ਸੱਚ ਤੇਰੇ ਦਿਲ ਨੂੰ ਰਾਤਾਂ ਨੂੰ ਦੱਸ ਮੈਨੂੰ ਨੀਂਦ ਕਿਉਂ ਨਾ ਆਵੇ ਤੂੰ ਠੀਕ ਹੈ ਕਿ ਨਹੀਂ ਮੇਰਾ ਚਿੱਤ ਘਬਰਾਵੇ ਕਿਉਂ ਇੰਨੀ ਪਰਵਾਹ ਨਾ ਦੇਵੀਂ ਤੂੰ ਦਗਾ ਮੇਰੇ ਦਿਲ ਨੂੰ ਸੋਚਾਂ ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ ਅੱਖੀਂ ਰੜਕੇ ਨੀਂਦਰ ਮੈਨੂੰ ਸੌਣ ਨਾ ਦੇਵੇ ਬੇਚੈਨੀ ਬਸ ਮੈਂ ਹੀ ਨਹੀਂ ਆ ਕੱਲਾ ਅੱਜ ਤੇਰੇ ਚੰਨ ਨਾਲ ਤਾਰੇ ਹੈ ਨਹੀਂ ਕੈਸਾ ਹੋਇਆ ਏ ਮਾਹੌਲ ਸਨਾਟਿਆਂ ਦਾ ਸ਼ੋਰ ਮੇਰੇ ਕੰਨ ਤੱਕ ਗੂੰਜੇ ਮੈਨੂੰ ਖਾਣ ਤੀਕ ਜਾਵੇ ਸਾਰੀ ਰਾਤ ਮੈਂ ਲਾਈਆਂ ਕਾਲ ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ ਮੈਂ ਖੁਦ ਵਿੱਚ ਖੋਈ ਜਾਨਾ ਆ ਮੈਨੂੰ ਲੱਭਣ ਵਾਲਾ ਕੋਈ ਨਹੀਂ ਕਿ ਜੇ ਅਜੇ ਆ ਕਿਉਂ ਫਿਰਦਾ ਆ ਅੱਖ ਹਜੇ ਤੀਕ ਤਾਂ ਰੋਈ ਨਹੀਂ ਹਜੇ ਟਾਈਮ ਨਾ ਕੁਝ ਵੀ ਹੋਇਆ ਏ ਹਜੇ ਰਾਤ ਵੀ ਮੇਰੀ ਖਲੋਈ ਨਹੀਂ ਤੈਨੂੰ ਆਪਣਾ ਕਹਿਣ ਦੀ ਗਲਤੀ ਮੈਂ ਹਜੇ ਕਿਸੇ ਦੇ ਕੋਲੋਂ ਲਕੋਈ ਨਹੀਂ ਪਿਆਰ ਹੋਇਆ ਡਾਵਾਂਡੋਲ ਕਰਾਂ ਹੁਣ ਕੀ ਕਿਤੇ ਲੱਭਦੀ ਨਾ ਲਈ ਕੋਈ ਰਾਤੇ ਦਿਖਾਵੇ ਸਾਰੀ ਰਾਤ ਮੈਂ ਲਾਈਆਂ ਕਾਲ ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ ਚੈਨ ਨਾ ਆਵੇ ਸਾਰੀ ਰਾਤ ਮੈਂ ਲਾਈਆਂ ਕਾਲ ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ
ਇਉਂ ਜਾਪੇ ਜਾਂ ਜਾਗਦਾ ਮੈਂ ਜਾਂ ਜਗਣ ਸ਼ਹਿਰ ਦੀਆਂ ਬੱਤੀਆਂ ਪਿਆਰ ਦੇ ਮਹਿਲ ਨਟਾ ਜਾਣ ਜੋ ਵਗਣ ਹਵਾਵਾਂ ਤਤੀਆਂ ਹੱਥੋਂ ਇਸ਼ਕ ਦੇ ਛੁੱਟ ਕੇ ਧਾਗੇ ਤੇ ਬਸ ਆਸਾਂ ਰਹਿ ਗਈਆਂ ਕੱਤੀਆਂ ਮੈਂ ਨਾ ਰਿਹਾ ਤੇਰੇ ਕੋਲ ਤੇਰੇ ਕੰਨ ਵਿੱਚ ਰਹਿ ਗਈਆਂ ਦਿੱਤੀਆਂ ਲੱਤੀਆਂ ਬਸ ਪੈਂਦੇ ਹੁਣ ਹਾਲ ਸਬਰ ਨਾ ਕੀਤਾ ਦਿਲ ਨਾਲ ਜ਼ਬਰ ਸੀ ਕੀਤਾ ਤੇ ਹੁਣ ਦਿਲ ਹੀ ਨਚਾਵੇ ਸਾਰੀ ਰਾਤ ਮੈਂ ਲਾਈਆਂ ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ ਸਾਰੀ ਰਾਤ ਮੈਂ ਲਾਈਆਂ ਕਾਲ ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ
ਸਾਰੀ ਰਾਤ ਮੈਂ ਲਾਈਆਂ ਕਾਲ
ਸਾਰੀ ਰਾਤ
ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ
ਸਾਰੀ ਰਾਤ ਮੈਂ ਲਾਈਆਂ ਤੈਨੂੰ ਕੀ ਅੰਦਾਜ਼ਾ ਮੇਰੇ
ਦਿਲ ਤੇ ਕੀ ਬੀਤੀ ਮੈਨੂੰ ਚੈਨ ਨਾ ਆਵੇ तुम हो पास मेरे, साथ मेरे हो तुम यूं, जितना महसूस करूं तुमको उतना ही पा भी लूं। तुम हो
बदली कभी कहीं कर दे तन गीला, ये है भी ना हो। किसी मंजर पर मैं रुका नहीं, कभी खुद से भी मैं मिला नहीं, ये गिला तो है मैं खफा नहीं। शहर एक से गांव एक से लोग एक से नाम एक फिर से चला मिट्टी जैसे सपने ये किताबी पलकों से झाड़ो फिर आ जाते हैं। इतने सारे सपने क्या कहूँ किस तरह से मैंने तोड़े हैं छोड़े हैं क्यों मेरे साथ चले मुझे लेके उड़े ये क्यों कभी डाल डाल कभी बात बात मेरे साथ साथ फिर दर दर ये कभी सहरा कभी सावन बनू रहा कभी दिन है रात कभी दिन दिन है क्या सच है क्या माया है दाता इधर उधर तितर बितर क्या है पता हवा ले ही जाए तेरी ओर खींचे तेरी यादें तेरी ओर। के मिलन की आस ओ नादा या निज़ामुद्दीन औलिया या निज़ामुद्दीन सरकार कदम बढ़ा ले हदों को मिटा ले आजा खाली पल में पी का घर तेरा तेरे बिन खाली आजा खाली पल में तेरे बिन खाली आजा खाली पल रंग रेजा रंग रेजा रंग रेजा
parameterizations of these joints. Great. You need more context to be able to make a good prediction about the next word. And then what you do is, for every node in the graph, you specify its conditional distribution given its parent. And so, which is essentially the same kind of generalized simple definition of condition, like a market assumption. So if these x words by a distribution of x values, well, if the variables are binary, then x1 can take two different values, 0 and 1. And for each one of them, you have to specify a distribution of x2, which will take you one parameter simple, 2, and so forth. 3 given x. The important one for now is going to be the first one, chain rule, though we're also going to use Bayes' rule later. But chain rule basically gives you a way of writing down a joint distribution as a product of potentially simpler objects, which are these marginals or conditional probabilities. And so this is how you would use it. You can always take a joint distribution over n variables and write it down as a product in this way as the probability of x1 times the probability of x2 given x1, the probability of x3 given x1 and x2, and so forth. Using chain rule, this is something you can always do. This is the kind of factorization that is used in autoregressive model, which is the first class of models that we're going to talk about, which is, again, the same thing that is used in, for example, large language models. And here the idea is that you can write down the probability of observing like a sequence of words. Let's say in a sentence, as the probability of observing the first word times the probability of observing the second word given the first one times the probability of observing the third word given the first two, and so forth. Now this is fully general. You can apply it also to pixels. Any collection of random variables can always be factorized this way. Now, how many parameters do we need if you use this kind of factorization? And it seems like maybe we've made progress because this object here is very complicated. But now P of x1, for example, is a simple object. It's a marginal distribution over a single pixel. So perhaps we've made progress here. So let's do the math. How many parameters do we need? It turns out that we still need an exponentially large number of parameters, unfortunately. And the reason is that it's kind of no free lunch. We haven't made any assumptions to get this factorization, so we cannot expect to get any savings. And you kind of see it here. Although the first distribution here is indeed simple, you can store it represented with a single parameter. Then how many parameters do you need for the second? Well, if the variables are binary, then x1 can take two different values, 0 and 1. And for each one of them, you have to specify a distribution over x2, which will take you one parameter. So P of x2 given x1 will take two parameters. One for the case where the first bit or the first variable is 0, and one for the case where it's 1. And then if you look at the P of x3 given x1 and x2, there are 4 possible values that x1 and x2 can take, so you need 4 parameters. So that's where you get this kind of geometric series, and that's where you get the exponential blow up. These last conditionals here are very expensive. Right, and so if you do the sum, you still don't get anything here. But it gives us a way to perhaps make progress. It's still a useful building block. And for example, one thing you can do is you can assume independence, conditional independence. For example, you might be willing to assume that the value of the ith plus one word is conditionally independent from the previous, given the ith word, the value of the ith plus one word is conditionally independent of all the previous words. Right, so this is kind of like a markup assumption. So if these x's maybe represent the weather, then you're saying the weather tomorrow is conditionally independent from the past given the weather today. And if you're willing to make this assumption, then you get big savings. What this means is that if you think about the definition of conditional independence, is that a lot of these conditional distributions will simplify. And so in particular, this probability of x3 given x1 and x2 becomes the probability of x3 given x2. So if you're predicting the third word, this is saying you just need to know the second word, you can ignore the first word. And if you're predicting the last word, you don't need to remember the entire sequence, the previous word is sufficient. And if you do that, then you get this nice expression where the conditionals are now simple. Like you're always conditioning on at most one variable. And so now we get big savings. Right? How many parameters do we need here? Yeah, something like that. This linear in n, basically, right? Depending on if there is a binary, this is the formula. So big savings, and now we have a much more reasonable model. This is much more reasonable than the full independence model. These Markovian models are quite useful in practice. But again, if you think about language or you think about pixels in an image, it's probably not good enough. You're probably not going to do a great job if you're trying to predict. If you think about it, your autocomplete in your phone, you're trying to predict the next word just based on the previous one and you ignore everything else. You can do okay, but it's not going to be great. You need more context to be able to make a good prediction about the next word. And so although there's an exponential reduction, maybe this assumption is still a little bit too strong. And so one way to kind of generalize this idea is to use something called the Bayesian network, which is essentially the same machinery in slightly more generality. The basic idea is again that instead of we're going to write down the joint as a product of conditionals, but instead of having these simple conditionals where it's always one variable given another variable, we're going to say we're going to use conditional distributions where the ith variable will depend on another set of random variables, which are the parents in this Bayesian network. And so intuitively, the idea is that we're going to try to write down the joint as a product of conditionals, but now the conditionals are a little bit more complex. Now each variable is allowed to depend on a subset of variables. It could be one, it could be more, so that buys you a little bit more flexibility. And the idea is that because we're using chain rule, as long as there is some kind of ordering that you've used to come up with this joint distribution by simplifying the kind of expression that you would get from chain rule, then this is kind of guaranteed to correspond to a valid model. Essentially, you can specify any conditional distribution you want on the right-hand side. Once you multiply them together, you're going to get a valid probability distribution on the left-hand side. That's sort of like the key intuition behind the Bayesian network. More formally, a Bayesian network is a data structure that you can use to specify a probability distribution. It's a graph-based data structure where basically there's going to be an underlying directed acyclic graph, which basically gives you the ordering in that chain rule factorization. So there's going to be one node in the graph for every random variable that you're modeling. So if you're modeling images, one node for every pixel. If you're modeling text, one word for every token or every word that you have. And then what you do is for every node in the graph, you specify its conditional distribution given its parent in this directed acyclic graph. And that's the graph is the structure. And then by specifying different conditional distributions for each variable given the parent, you get different parameterizations of these joints. Specify a probability distribution. That's sort of like the key intuition behind the Bayesian network. More formally, a Bayesian network is a data structure that you can use to specify a probability distribution. It's a graph-based data structure where basically there's going to be an underlying directed acyclic graph, which basically gives you the ordering in that chain rule factorization. So there's going to be one node in the graph for every random variable that you're modeling. If you're modeling images, one node for every pixel. If you're modeling text, one word for every token or every word that you have. And then what you do is for every node in the graph, you specify its conditional distribution given its parent in this directed graph. And that's the graph is the structure. And then by specifying different conditional distributions for each variable given the parent, you get different parameterizations of these joints. And the claim is that basically this is a valid probability distribution. And the reason is that it's essentially the same trick we did for the Markov model. You start with a given a directed acyclic graph, you can always come up with an ordering. So you can just do topological sort on the graph, you get an ordering, you can apply chain rule, you factorize with respect to that ordering, then you simplify the conditionals based on this some conditional independence assumption. And that gives you a potentially compact data structure. It depends on how many parents, how dense the graph is, but this can give you savings. Again, the challenge is that we have this joint distribution, and it takes too many parameters to represent this object. But if these conditionals are relatively simple, so you don't have too many parents for each variable, then these conditionals are simple enough that you can store this object. You can learn these parameters from data and so forth. So it's kind of like exponential in the number of parents that you have for each variable. So if you make a very dense graph, you're going to get a very expressive class of models, and you're not going to get big savings. If you use a chain graph where there's only one parent per node, then you get the Markov assumption that we had before, and there are things in between. For example, okay, this is just a, what does it mean? A directed cycle would be something like this. So you need to make sure that there's no directed cycle, which means that there's an ordering, and it means you can use chain rule. This is an example of a very simple Bayesian network. Here the idea is that you have these 5 random variables representing the difficulty of an exam, the intelligence of a student, the grade that you get, so forth. And there's a joint distribution over these 5 random variables, which is obtained as a product of conditional distributions of each variable given the parent. And so for this particular graph, this node doesn't have any parent, so you just write the marginal probability of that node. This node doesn't have any parent, so again, it's just the probability of getting different intelligence values. The grade has 2 arrows incoming from difficulty and intelligence. And so what you're saying is that the grades that you see depend essentially on the possible values of the difficulty of the exam and the intelligence of the student. And so you can basically write down the joint as a product of conditionals that would look like this. And in this case, this might be more economical than representing the joint because you basically just have to specify these tables. These conditional probability distribution. You only need to work out basically how these random variables are related to each other locally with respect to this graph. You only need to know that. So you can basically write of the you're saying is that the grades that you see depend essentially on the possible values of the difficulty of the exam and the intelligence of the student. And so you can basically write down the joint as a product of node. This node doesn't have any parent, so again, it's just the probability of getting different intelligence values. The grade has 2 arrows incoming from difficulty and intelligence. And so what you're saying is that the grades that you see depend essentially on the possible values of the difficulty of the exam and the intelligence of the student. And so you can basically write down the joint as a product of conditionals that would look like this. And in this case, this might be more economical than representing the joint because you basically just have to specify these tables, these conditional probability distributions. You only need to work out basically how these random variables are related to each other locally with respect to this graph. You only need to know how to assign grades given different values of difficulty and intelligence, but you're kind of like breaking down the complexity of the joint in terms of smaller local interactions between the random variables. And again, by making this assumption that kind of like the global dependencies can be broken down into simpler local dependencies, you get benefits because these conditionals are potentially much smaller, much simpler, easier to represent. And the idea is that assuming this factorization is the same as assuming conditional independencies. Right? And you can kind of see it here. We have this kind of factorization for the joint, which is implied by this graph. In general, we know that you can always have a more complicated factorization where every variable depends on all the variables that come before it in some ordering. Right? So in general, you would have to specify the probability of having a certain difficulty for the exam. You would have to specify the probability of some intelligence value given the difficulty, the probability of G given IND, the probability of the SAT score given everything else, and so forth. Now, if you're willing to assume that the intelligence of the student does not depend on the difficulty of the exam, then you can start simplifying these conditionals, and they become like the ones you see above. So if you want to, for example, the SAT score, only depends on the intelligence, and you don't need to know the difficulty of the exam. You don't need to know the grade in the other exam to figure out the SAT score. And so this factorization basically corresponds to a bunch of conditional independencies. We're saying the difficulty and the intelligence are independent of each other. The SAT score is conditionally independent from the difficulty and the grade given the intelligence, and so forth. And so Bayesian networks are basically a way to simplify complicated distributions based on conditional independence assumptions, which are more reasonable than full independence assumptions. Now, to summarize, we can basically use Bayesian networks as a tool to factorize distributions and write them down as a product of conditionals. You get the joy by multiplying together the conditionals. You can sample by basically going through the ordering. In this class, we're actually not going to be going this route. So that's the route that you're going to take if you want to build a probabilistic graph, like a graphical model, a PGM, a probabilistic graphical model. In this class, the graphical model will still be using a little bit of graphical models notations, but the graphical models are going to be relatively simple. They typically involve 2 or 3 random variables, random vectors. And instead, we're going to be making other kinds of like a softer notion of conditional independence, which is going to be essentially this idea of let's use neural networks to try to represent how different variables are related to each other. So we'll still have somewhat the flavor of a Bayesian network, but it's going to be a little bit of a softer kind of constraint between the variables. Now, obviously, this was a bit of a crash course, but again, we're not going to be leveraging these things too much. We're going to use a little bit of graphical models notation and a little bit of characteristic graphs for some of the graphical models, but nothing too heavy. We're going to be using different sort of assumptions and different sort of modeling ideas to build deep generative models. And that's going to be, again, inspired by the use of neural networks for, let's say, classification or other kind of discriminative tasks that you might have seen before. And so now it's a good time to kind of like try to get a sense of what's the difference between building a generative model versus building a usual discriminative model, and how do we get the ideas from the things that we know work, when you're doing, let's say, image classification or these more standard kind of like machine learning problems, and translate them back into the generative modeling world. And in order to see that, let's see, again, kind of like one example where you could try to, we're going to use a simple kind of like generative model to do to solve a discriminative task, and we'll see how that model is more standard. We know it's usual discriminative model, and how do we get the ideas from the things that we know work, when you're doing, let's say, image classification or these more standard kind of like machine learning problems, and translate them back into the generative modeling world. And in order to see that, let's see again kind of like one example where you could try to, we're going to use a simple kind of like generative model to do to solve a discriminative task, and we'll see how that will differ compared to a traditional approach based on, let's say, a neural network. So let's say that you want to solve a task where you're given a bunch of images, a bunch of emails, and the goal is to predict whether or not this email is spam. So there's a binary label Y that you're trying to predict. And you're doing it using a bunch of features, xi, and let's say the features are just binary and they're on or off depending on whether or not different words and some vocabulary appear in the email. And the usual assumption is that there's some underlying data generating process, and so there's some relationship between the different words that you see in the email, the x's, and the y variable, which is the label you're trying to predict. So one way to approach this is by building a Bayesian network. This is a basic classifier called the naive Bayes classifier, which is basically going to say, we want to model this joint distribution. This joint distribution has too many variables. We cannot afford to store it to learn the parameters from data. So we're going to make conditional independence assumptions, and we're going to assume that the joint can be described by this directed acyclic graph. If you are willing to make this kind of like Bayesian assumption, what this means is that the features, the words, the xi's, are basically conditionally independent given the label, given the y. If you're willing to make this assumption, then you're able to factorize the joint, which is usually complicated, as a product of conditionals. So you can write it as the p of y because y doesn't have any parent. And then the probability of one variable given its parent, probability of this variable given its parent, and so forth. Which means that you can basically, according to this very simplified model of the world, you can generate a data point by first choosing whether or not it's spam, and then choosing whether different words appear in the email based on whether the email is spam or not. And once you have that kind of model, what you can do is you can try to estimate the parameters of this model from data. So you can try to estimate these probabilities by looking at how frequently you see different words in different types of emails. And then you can do classification, because at the end of the day, what you're trying to do is you're trying to classify whether or not a new email is spam or not. And you can use Bayes' rule to write down the conditional distribution of y given x. So given a new email, you observe which words are there and which ones are not, and you can try to compute the probability. You can try to estimate this to estimate the parameters of this model. And once you have that kind of model, what you can do is you can try to estimate the parameters of this model from data. So you can try to estimate these probabilities by looking at how frequently you see different words in different types of emails. And then you can do classification, because at the end of the day, what you're trying to do is you're trying to classify whether or not a new email is spam or not. And you can use Bayes' rule to write down the conditional distribution of y given x. So given a new email, you observe which words are there and which ones are not, and you can try to compute the probability y by basically using Bayes' rule. Rule to write down the conditional distribution of spam or not. What you're trying to do is you're trying to classify whether or not a new email is spam or not. And you can use Bayes' rule to write down the conditional distribution of y given x. So given a new email, you observe which words are there and which ones are not, and you can try to compute the probability y by basically using Bayes' rule. Probability of x comma y divided by the probability of x, essentially, which is what you have at the denominator. And if you've done a good job at estimating these parameters, this thing will, and to the extent that the assumption is true, this conditional independence assumption is true, this model might perform reasonably well at predicting the label y given the features x. The challenge, of course, is once again that perhaps these conditional independence assumptions are not that great. If you think about it, you're saying that different words appear in an email independently of each other. So once you know why, basically knowing whether a word appears or not doesn't help you predict whether some other word appears in the email or not, which is probably not reasonable. Nevertheless, this model tends to work okay in practice. So even though the assumption is not quite true, it might give you reasonable results in practice. Now, how does this fit into the discriminative versus generative kind of model of the problem? So at the end of the day, we're trying to model this joint distribution between features and a label y. And using chain rule, we can write it like this as the probability of the label times the probability of the features given the label. This is exactly what we've done in the naive Bayes model that we just saw. Alternatively, you can use chain rule based on a different ordering, and you can say, I can write it as the probability of observing this feature vector times the probability that that particular feature vector has label y. And joint distribution between features and a label y. And using chain rule, we can write it like this as the probability of the label times the probability of the features given the label. This is exactly what we've done in the naive Bayes model that we just saw. Alternatively, you can use chain rule based on a different ordering, and you can say, I can write it as the probability of observing this feature vector times the probability that that particular feature vector has label y. And so these are basically two Bayesian networks that capture the same joint distribution, one where we have y and then x. X, and then one where we have x and y. And the second one is basically the one that you deal with when you think about usual discriminative models. Like if you think about it, at the end of the day, if all you care about is predicting whether a new data point has label 0 or 1, all you care about is P of y given x. And so the second kind of modeling approach, where you're modeling P of y given x directly, might be much more natural. In the left model, we were specifying P of y, we were specifying P of x given y, and then we would compute P of y given x using Bayes' rule. While in the second model, you have access to P of y given x, the probability of this variable given its parent, directly. And so the idea is that if you know that all you care about is P of y given x, then there is no point in trying to learn or model y given x directly. And so the idea is that if you know that all you care about is P of y given x, then there is no point in trying to learn or model or deal with this marginal distribution over the features. Right? If you know that you're always ever going to be given an email and you just try to predict why do you bother trying to figure out what kind of feature vectors x you're likely to see? Right? P of x here will basically be a distribution over the features that your model is going to see. If you know you don't care because you just care about predicting y from x, then you don't even bother modeling P of x. And so that's more convenient. And that's why typically the kind of models that you're building, that you use in machine learning, they don't bother about modeling the distribution of the features. You just bother about modeling the relationship between the label and the features x. While in a generative model, it's the opposite. You're basically modeling the whole thing. You're modeling the full joint distribution. And so the discriminative model is basically only useful for discriminating y given x, while the generative model is also able to reason about its inputs. It's able to reason about the full relationship between x and y. And so now, there is still no free lunch in the sense that if you think about it, it's true that you can do these two factorizations. You can use either factorize as P of y and then P of x given y, or you can do P of x and then P of y given x. But in both cases, you end up with some of these conditions which are pretty complicated. right? So in the generative model, you have a vision. If you were to actually unpack the fact that x is random vectors, you have a bunch of individual features that you have to deal with. The two graphical models corresponding to the two chain rule factorizations would look like this. In the generative view of the world, you have y, and then you have all the features. In the discriminative view of the world, you have all the x's first, and then you have y and x. And you still need to deal with the fact that you have a lot of x's. You have potentially a lot of features that you have to take into account when you're predicting y. And so, in the generative modeling world, P of y is simple, but then you have a bunch of these variables here that have a lot of parents. So there's a lot of complexity that you have to deal with when you need to decide, what are the relationships between the features. In the discriminative modeling world, this first, and then you have y and x. And you still need to deal with the fact that you have a lot of x's. You have potentially, and you still need to deal with the fact that you have a lot of x's. You have potentially a lot of features that you have to take into account when you're predicting y. And so, in the generative modeling world, P of y is simple. In the view of the world, you have all the x's first, and then you have y and x. And you still need to deal with the fact that you have a lot of x's. You have potentially a lot of features that you have to take into account when you're predicting y. And so, in the generative modeling world, P of y is simple. But then you have a bunch of these variables here that have a lot of parents. So there's a lot of complexity that you have to deal with when you need to decide, what are the relationships between the features. In the discriminative modeling world, it's true that you're making some progress because maybe you don't need to model all these relationships between the x variables, but you still need to be able to model how y depends on all the x's. And y has a lot of parents. So again, that conditional distribution is potentially very complicated. So one way to make progress is to say, okay, let's make conditional independence assumptions. So in general, you would have something, a generative model would have to look like this. So you would have to be able to capture all sorts of dependencies between the x's and the y. If you're willing to make simplifying assumptions and say, things are conditionally independent, then you basically chop some edges in the graph, and you end up with something that is much simpler. Remember, the less parents the variables have, the simpler the relationships between the random variables are, the simpler the model is. And so you're saying, once I know y, I can basically figure out the values of the x variables, and there is no relationship between them. That's one way to make progress. Obviously, it's a strong assumption. It might or might not work in the real world. In the discriminative model, you still need to be able to model this conditional distribution of y given all the x's. And again, that's not straightforward because if you think about all these features here, let's say they're binary, there are 2 to the n possible feature vectors that you have to deal with. And for each one of them, you would have to specify, like when you look at this last conditional here, it's the same as before, right? You're conditioning on a lot of variables. There are 2 to the n possible combinations of those x variables, and you would have to, in full generality, you would have to assign a different number, a different value for the probability of y for each one of them. And so again, kind of like the conditional distribution of y given all the parents is not easy to deal with even in a discriminative model. So the way you make progress usually in a discriminative model is to assume that the dependency is not fully general and it somehow takes a particular functional form. So it's true that this x vector can take many, many different values. And if you were to use a big table, that table would have 2 to the n possible rows. So you would not be able to store that, you would not be able to learn it from data, you would not be able to use it. But what you can assume is that there is some simple function that you can use to take x and map it to a probability value. Right? And so the assumption that you have to make here to make progress is to assume that there is some simple function f that you can apply to the different values that the x variables can take, and that will map it to this number that you care about, which is the conditional probability of y given x. And there's many different ways to do it. One way is to there's some constraints here, and one way to do it is to do what's done in logistic regression, for example. So the idea is that, and that's why it's called regression, is that essentially it's not a table. There's going to be some kind of function that will take different values of x and will regress them to probabilities for y. And it's not an arbitrary kind of like regression problem. because what we're doing is we're trying to map these x's to conditional probabilities. And we know that conditional probability is a number that has to be between 1 and 0. Like, it doesn't make sense to say, oh, I fit in a certain feature vector x in the spam classification is a bunch of indicators of whether different words appear in the email. If this function gives me a value of -1, it doesn't make sense, right? Because we know the probabilities are numbers between 0 and 1. So there are some constraints on the kind of on this regression problem. In particular, we want the output to be between 0 and 1. We want the dependency to be simple but reasonable. If it's too complicated, it's a table, a lookup, then you're back to the previous settings, you don't gain anything. So somehow you want a simple dependency, but it's sufficiently rich that it captures real ways in which changing x should change the probability of y. And one way to do it is to assume that there is some vector of parameters, alpha in this case, and then perhaps what you can do is you can assume some kind of linear dependence, where you basically take a linear combination of these x's, these features, weighted by these coefficients alpha, and you try to do this as regression. It's kind of like linear regression at the end of the day. You take different values of x and you map them to different outputs. Now, by itself, this wouldn't work because remember, we have to assume that these numbers are between 0 and 1. But that's something easy to fix. You can just transform that value with a function that rescales things and maps them to be between 0 and 1. For example, you can use the logistic function or the sigmoid. And if you do that, then you get what's known as logistic regression. It's a way to model a conditional distribution of y given x, where you're assuming that that conditional distribution takes a specific functional form. You're assuming that given different values of x, you can linearly combine them based on some vector of coefficients alpha, and then you pass them through the sigmoid function, this S-shaped function, that will take z values between -infinity and +infinity, and will rescale them to be between 0 and 1. So then they're valid probabilities. And that's another way to make progress. It's another way to deal with the fact that, in general, you cannot represent this complicated dependency between y and all the x variables as a table. You have to either assume that there is conditional independency, so things don't even depend on some of the inputs, or you assume that there is some kind of specific functional form that allows you to compute these probabilities. And this is one such assumption, is the logistic regression assumption. Question, yeah?
When you make the linear dependence assumption, is that basically saying that the Bayesian network, that the x's are independent, and that they're not related to each other, and then is that also equivalent to just having like the joint distribution being described by the product of the marginals?
It's actually, so the question is whether this implies some conditional independence assumptions, and the answer is the other way around. That basically, if you assume the naive Bayes kind of factorization, then the conditional distribution of y given x will have this functional form, but not vice versa, not necessarily vice versa. And so, in some sense, you're making a weaker statement about the relationships of the random variables, which is why this model is stronger in practice. You're assuming less about how the random variables are related. So to the extent that you have enough data to really learn the relationship, you're better off with this model because you are assuming less. If you have very limited data, you might be better off with a naive Bayes model because you're making a strong assumption, but the prior helps you more because you don't have enough data to figure out how things are really related to each other. But this is kind of like a different sort of assumption. You're really saying there's some functional form that tells you how the random variables are related to each other.
Yeah. That doesn't imply that your joint is a product distribution.
So the question is, does this imply that the joint is a product distribution? You're just working at the level of single conditional. So what we'll see is that, in fact, an autoregressive model, a deep autoregressive model, will essentially be built by assuming that there is a chain rule factorization and then modeling the conditionals using this kind of functional relationship, maybe a linear regression model or a deep neural network. And that's how we'll build the first type of useful deep generative model. But this by itself is just for a single condition. So it's not a statement about the joint. It's just saying, I'm not even going to care about modeling the P of x. I'm not going to reason about the inputs that my logistic regression model is going to see, because at test time, I'm always ever going to be, somebody's going to give me the x's. So I don't need to bother about figuring out how the different words are related to each other. I'm only going to bother about modeling how to predict y from x, and that's already hard, but I'm going to do it based on this simplifying assumption. And by assuming that you're making this linear dependence, again, you're making some assumptions which might or might not be true in the real world, right? So in particular, this is a relatively simple kind of dependency that you're assuming between y and x. And so what you're doing is you're saying that, let's say if you have two features, x1 and x2, then you're basically saying that equal probability contours are straight lines. So there's some straight lines such that all the points that lie on those straight lines have the same conditional probability for y. Or it also means that the decision boundary, so if you're using a threshold to decide whether a variable belongs to class 0 or 1, is going to be again a straight line. So all the points on this side of the line are going to be positive, all the other ones are going to be negative. And specifically, basically, it means that the thing about how the probability changes as you change x and y, it has a very specific kind of like functional form. It looks like this S kind of thing, where the way you change the probability as you change x, the way the probability of y given x changes as you change x, has a very specific functional form. If you think about the lookup version of this, it would be an arbitrary function. Here you're saying, no, I'm willing to assume that it takes a very specific, relatively simple functional form, which again might or might not be true in the real world. Maybe the probability of y given x should have a very different shape, and then this model is not going to work well. Kind of like before, we were assuming conditional independence might or might not be true in the real world. Here we're assuming a specific functional form, which might or might not be true in the real world, and that determines whether or not your model is going to work well or not in practice. And so again, basically, these are dealing with this issue of modeling distributions over high-dimensional spaces. You have to make assumptions. Naive Bayes is one way to make progress. Conditional independence assumption. The logistic regression model does not make that assumption explicitly. It does not assume that the features are conditionally independent given the label. So it's a little bit more powerful. When you think about the spam classification, there might be two words in your vocabulary, like a bank and account. Knowing whether one appears in the email, so knowing x1 tells you a lot about whether x2 appears in the email. But the naive Bayes model assumes that it doesn't help. So that assumption is clearly wrong in the real world. The discriminative model does not make that assumption explicitly, right? So let's say that in your data set, these two words always appear together. So whenever there's bank, there's also account. The naive Bayes model is forced to assume by construction that they are independent. So whenever you see that both of them appear is going to double count the evidence. It's going to think both of them are telling me something about whether this is spam or not. I know that they're independent, so if I see both of them at the same time, I'm doubly confident that maybe this is spam. The logistic regression model can actually just set one of the coefficients to 0, and it doesn't double count the evidence. So you can kind of see that you're making kind of like a weaker assumption, and it's actually powerful, and that's why this logistic regression model tends to work better in practice. However, the issue is that one thing you cannot do, let's say if you have a logistic regression model, is that you cannot reason about your own inputs. So the only thing you can do is you can map x to y. But you cannot, let's say somebody gives you, the same thing happens also in image classification. So let's say that you have a model that is predicting a label of an image, given the image x. That's the only thing you can do, predict y from x. So if somebody gives you a new image where some of the pixels are missing, there is no way for you to kind of impute the missing values because you don't know what's the relationship between the x variables. You didn't model p of x at all, you only model p of y given x. And so that's one thing you cannot do with a discriminative model that you can do with a generative model. A generative model is kind of like trying to model the full joint distribution between y and x. And so at least in principle, as long as you can do inference, as long as you can compute the right conditionals, the modular computational issues, you have enough information to predict anything from anything. So you can impute missing values, you can do more interesting things. But it's a harder problem because you're not only modeling the relationship between how to predict y from x, you're also modeling the full thing. You're modeling the relationship between the features, between the inputs as well. Okay, and then how do neural networks come in here? Well, as we said, the issue with one of the issues with the logistic regression model is that you're still making some kind of simplifying assumption on how y depends on x. Right? We're assuming that there is this linear dependence. You take the x, the features, you combine it linearly, you pass them through the sigmoid, and that's what gives you y, which again might not be true in the real world. And so one way to get more expressive, make even weaker assumptions in some sense, is to basically allow for some nonlinear dependence. Right? You could say, instead of directly taking the x features and map them by linearly combining them to a probability value, I'm going to compute some features of the input x. Perhaps I do it by taking some kind of like a linear combination of the features and then applying a nonlinear function to each value that I get out of this. And then I'm going to do linear regression on top of these features. Right? So instead of directly applying linear regression to x, first I transform x by multiplying it by a matrix A and then shifting by some vector of coefficients b, and then I do logistic regression on these features. And that's essentially a very simple kind of like one-layer neural network. Instead of predicting directly based on x, I transform x to get these features h, and then I do linear regression based on that. And that's strictly more powerful because now I'm allowed to do more complicated computations. And if you think about that graph, that shape of that function of how y depends on x, now I have two more parameters. I have this matrix A, this vector of coefficients of biases b, and I can use this to change the shape of the function. I can get more complicated relationships between y and x. And so there's a trade-off here. I'm using more parameters to represent this conditional distribution. I no longer have just a vector of coefficients alpha. I also have a bunch of matrices for the previous kind of like layer in the neural network, but that gives me more flexibility in predicting y from x. And of course, you can imagine kind of stacking this many times, and then you can use a deep neural network to predict y from x. Was there a question? Yeah.
Why do you still need alpha here?
I guess you still want to, have a, you still want to make it deeper, I guess, and you want to map it to a scalar eventually. So I guess ax plus b is a vector, and I'm trying to map it to a scalar, so I use this alpha vector. But just to making it explicit that it's a strict generalization of kind of what I had before. But you do want it to be eventually mapped to a single scalar value. So that would be kind of like the softmax at the end. Although this one is the binary, so it's not quite a softmax, but it's essentially the softmax at the end of a neural network that maps the output to a valid probability value. So if y were a categorical variable, then that would exactly be the softmax at the end. Okay, so and then essentially what you can do is you can repeat this multiple times, and you can get a more expressive way of capturing the relationship between some y variable and the input variables x. And this is going to be the building block that we're taking advantage of this fact that neural networks seem to work very well at solving these kind of prediction tasks, and we're going to combine them to build generative models. And the simplest way to do it is to use chain rule and then use neural networks to represent each one of those conditionals. And that's essentially a neural autoregressive model, and essentially that's what large language models do. They use chain rule, and then they represent the simplified conditionals by assuming that you can model them using a neural network. So you can predict the next word, given the previous ones, using a neural network. But there's going to be other ways, and when we see other classes of generative models, they're still kind of going to use these kind of ideas, but maybe we're going to combine them in different ways, and we're going to get different types of generative models. So that's kind of like the story. There's the chain rule factorization, which is fully general. So given a joint, you can always write it as a part of conditionals with no assumptions. In a Bayesian network, you're going to try to simplify these conditionals somehow by assuming that the variables are conditionally independent. So whenever you're trying to predict x4, you don't really need x2 and x3, you just need x1, for example, which is usually too strong, and this doesn't work on high-dimensional data sets, on images, text, the kind of things we care about. The one class of deep generative models, a very successful one, conceptually, that's this. It just replaces all these conditionals that we don't know how to deal with neural networks. And you can do different architectures, but fundamentally, that's the whole idea. We're going to use a neural network to predict what's the fourth word given the first, the second, and the third. And again, there's no free lunch in the sense that what we're giving up is we're assuming that there's some relationship, that these conditional distributions can basically be captured by a neural network, which might or might not be the case in practice. But that's sort of like the one way to not be the case in practice. But that's sort of like the one way to get the case in practice. Network, which might or might not be the case in practice. But that's sort of like the one way to get tractability, to the extent that these neural networks are not too big, and somehow you're able to tie them together. You can see that sort of like you need a different neural network for every position in the sequence, which would be very tricky. So somehow you need to figure out a way to tie together the weights of the neural network, so this can be done in practice. But ideally, this is sort of like the one way to get a degenerative model.
In the Bayesian last factor should be x4 given x3, right?
Yeah, it could be anything, I guess. Depends what's the shape of the neural network. If you were to do a Markov model, it should be x3. Yeah. But you could say that maybe the fourth word is completely specified by the first one. That would, and you don't need the second and the third don't help you in predicting the fourth and the first, which is probably a very weird assumption. It wouldn't work in practice, but the underlying idea is that you're going to simplify those conditionals by dropping the dependence on some variables, and that gives you a Bayesian network. Depending on which variables you drop, you're going to get different graphs. If you were to not drop any variable, you get this. You get a fully general model, and that makes no assumptions. So that's fully general, but it's too expensive because these conditionals are too. Whenever you're conditioning too many things, that conditional distribution is too complicated, and you cannot store it, you cannot learn it, so you cannot actually use it in practice. Cool. The last thing I wanted to mention is how to deal with continuous variables. So we often want to model not just discrete data, but actually data that's more naturally thought of as continuous. So taking values over the whole real axis. And luckily, the machinery is very similar. So here, instead of working with probability mass functions, we work with probability density functions. And here you can start to see how the idea of working with tables already doesn't work. Because kind of like there's an infinite number of different values that x can take. You cannot write down a table that will assign a number to each one of them. So you have to basically assume that there's some functional form, there's some function that you can use to map different values of x to a scalar. And for example, you can assume that x is Gaussian, which means that there is a relatively simple function that depends on two parameters, mu and sigma, and then you can plug them into this expression, and you get back the density of the Gaussian at any particular point x. Where mu and sigma here are the mean and the standard deviation of the Gaussian. Or you could say, okay, maybe a uniform random variable. Again, this is another kind of like relatively simple function. That you can use to map x to densities. Uniform distribution over the interval between a and b, we have that kind of functional form, etc. And the good news is that, again, we often care about modeling many random variables, which could be continuous or maybe a mix of continuous and discrete. In this case, we care about the joint probability density function, and the same kind of, for example, you cannot learn it, so you cannot actually use it in practice. Cool. The last thing I wanted to mention is how to deal with continuous variables. So we often want to model not just discrete data, but actually data that's more naturally thought of as continuous. So taking values over the whole real axis. And luckily, the machinery is very similar. So here, instead of working with probability mass functions, we work with probability density functions. And here you can start to see how the idea of working with tables already doesn't work, because kind of like there's an infinite number of different values that x can take. You cannot write down a table that will assign a number to each one of them. So you have to basically assume that there's some functional form, there's some function that you can use to map different values of x to a scalar. And for example, you can assume that x is Gaussian, which means that there is a relatively simple function that depends on two parameters. Mu and sigma, and then you can plug them into this expression, and you get back the density of the Gaussian at any particular point x, where mu and sigma here are the mean and standard deviation of the Gaussian. Or you could say, okay, maybe a uniform random variable. Again, this is another kind of like relatively simple function that you can use to map x to densities. Uniform distribution over the interval between a and b will have that kind of functional form, etc. And the good news is that, again, we often care about modeling many random variables, which could be continuous, or maybe a mix of continuous and discrete. In this case, it could be a function that you can use to map x to densities. Uniform distribution over the interval between a and b will have that kind of functional form, etc. And the good news is that, again, we often care about modeling many random variables, which could be continuous, or maybe a mix of continuous and discrete. In this case, we care about the joint probability density function, and the same kind of, for example, a joint Gaussian would have that sort of like functional form. So now x is a vector of numbers. And the good news is that the whole machinery chain rule, Bayes rule, they all still apply. So for example, we can write down the joint over PDF over probability density function over three random variables as a marginal PDF over the first one, a conditional over the second given the first, and so forth. And this is useful because we can, again, mix and match. We can use Bayesian networks, or we can use neural networks plus Bayesian networks in different ways to get different types of generative models. So for example, you can get a mixture of two Gaussians using a simple Bayesian network with two random variables, z and x. So the Bayesian network has two random variables, z and x. X has z as a parent, z doesn't have any parent. And so what it means is that the joint over x and z can be factorized as the probability of z times the probability of x given z. And for example, you could say z is a Bernoulli random variable with parameter p. So z is binary, it's either 0 or 1, and you choose a value with probability, with flipping a biased coin with probability p. And then condition on z, you choose a value for x by, let's say, sampling from a Gaussian. And because z can take two different values, there's actually two Gaussians. There's one Gaussian versus one for this latent z variable. And then another example, there's a mix and match z, and then maybe a fixed standard deviation. Not just another example. A more interesting one is the variational autoencoder, which we're going to cover in depth in future lectures. But at the end of the day, a variational autoencoder is this Bayesian network with two nodes, z and x, and the assumption is that z is sampled from a Gaussian. So p of z is just a simple Gaussian random variable. And here you see how we're going to mix and match Bayesian networks and neural networks. Given z, x is again a Gaussian distribution, but the mean and the variance of this Gaussian are the outputs of some neural network, or two neural networks, mu theta and sigma phi, which depend on z. So the sampling process is kind of like a generalization of the ones you see before, where again you first sample z, and then you feed z into a neural network that will give you, you see how kind of like you take these ideas and try to mix and match them. There's a little bit of Bayesian network, a little bit of chain rule, a little bit of neural networks to represent complicated conditionals, but everything can be stitched together, and that's how you get different kinds of generative models. And yeah, just as a note, even though mu and sigma could be very complicated, the conditional distribution of x given z is still Gaussian in this case, right? So there are some kind of trade-offs that you have to deal with. And yeah, this is it for today, and then the next we're going to talk about autoregressive models.